Well, good morning, everyone. It's 10 o'clock, so I guess we better get started. Did everybody get an email reminder of this lecture? Did you receive an email reminder? Oh, don't do that. I didn't receive either one of them. In any case, some of you know me, some of you don't. I'm Phyllis Saarinen, a former resident of Oak Hammock. And I'm very pleased this morning to introduce Associate Professor May Khanna, who is the inaugural Assistant Dean for Entrepreneurship and Innovation of the College of Medicine at UF. She joined the College of Medicine in late 2023. As Assistant Dean, she mentors the entrepreneurial interests of the next generation of medical scientists and supports innovative approaches in academic research, such as interdisciplinary, team-based approaches to public health priorities. And what you see on the screen is members of her laboratory. In her academic pharmacology career, she has co-founded 3 research firms, Regulonics, Regenerix, and Eternum Analytics. Now at UF, she directs the May Khanna Laboratory, researching the development of small molecule drugs for neurodegenerative diseases of concern to all of us, such as ALS, Alzheimer's, and Batten disease. The laboratory currently has 4 active grants in which she is named as the principal investigator. She's funded by NIH, Department of Defense, Batten Foundation, the Lehrman Funds, and UF Startup Funds. So I'm very pleased to welcome Dr. Khanna.
Thank you so much. Appreciate it. Appreciate being here. I guess I was told that you have to let me speak until the end and ask questions, and I actually don't believe that. I think you can interrupt me at any point. Please do. I'm much more of a I sort of feel it's much more fun if we're both involved in this, right? This is me telling you about what I do, but sometimes you have a burning question, you should absolutely ask it. Don't wait for me to be done until the end. So what Phyllis asked me to do is to kind of talk to you about two specific things. How do I approach this innovation entrepreneurship position at the College of Medicine through the Office of Research, as well as how do I a little bit about my research. And so I'll talk about both. Feel free, again, please do interrupt me. I have absolutely no problem. I'm used to this. I do this all the time. It's part of what we do. So I thought I'd start out, I always do actually start out my talks with representing, I represent the people who do the research in my lab. And so these are the group here, and where you might see logos with their pictures, such as David. There is the Eternum Analytics logo. Nilofar has a logo next to it. She's about to start this company known as RNA Thera. Jonathan co-founded Regenerix, where we're developing a small molecule for Alzheimer's disease. Oh, of course, yeah. I'm a very fast speaker, and I've had a lot of coffee, so. Okay, I'll slow down. See, that's great. You gave me some feedback. I love it. So Eternum is probably one of the funniest, I don't know if it's a funny story, but David came to me when he was an undergrad and he started working in my lab. And about maybe 3 months into it, my postdoc came to me and said, look, David is just he's just not performing as he should. I think we need to let go of him. And so I had a conversation with him and I said, I'm sorry, David. And he jokes that I fired him. I couldn't possibly fire him. He was volunteering. So I was like, look, you have to go figure out your priorities because clearly there's something wrong. You're not doing something right here. So David goes off and I had said, but I'll leave the door open because you are really one of the smartest kids I've met. And so I'd like to leave it open. He goes off, and then a year later, he writes me this really sweet email where he says, hi, Dr. Khanna, this is David Donald Scott. Do you remember me? I worked in your lab a year ago. Can I please come back to the lab? And I said, absolutely, come on back. And he ended up finishing his undergraduate degree, ended up getting his PhD in my lab. And then in addition to getting his PhD, towards the end of his PhD, he realized that, wait, we could there is this really interesting, so cannabis is legal in Tucson, but a lot of people test it in a really terrible way, right? There is so much money into this company. And there is the concern that you, especially for patients who have cancer and so on, if you're not testing it properly, if it's unethically tested, it's a really major issue. So David felt that, look, we actually have an opportunity to start this company. What do you think? And I was like, oh, I'm not really sure. But so then we find out more, and I get excited because there's actually science behind it, and there's actually really could be medicinally important, but not tested properly by those who are doing it. So we launched the company. We launched Eternum, and David is now, I actually was the CEO for a long time, and I finally actually gave him the CEO position, and he's now the CEO of the company. So, and this is a kid who basically was a first generation, none of his mom was an alcoholic, none of the, that part maybe we shouldn't tape and put back, but had some issues, right, in the background, but then went off and did incredibly well and is extremely successful in the company, knock on wood, is doing pretty well. Oh, okay. Am I really that sort of non-understandable? Am I speaking too fast? All right. So that's been, I just wanted to kind of point out to the stories that are the people that are coming from my lab, where I put an emphasis in the research, but then tremendously important to me is the ability to actually to launch off something that is significant to society, right? And it's always important to me to remind the kids in the lab, because often as someone who's in my lab, we have undergraduate students, we have graduate students, we have students who've gotten their PhDs, and we have students who are, and I have more senior people who work in the lab. So really, I cover a span of very many different levels, and even in summer, we'll have high school students come in. So truly, from 15 on to 60, you'll have people in the lab working together and working on a common cause of trying to find drugs for neurodegenerative diseases. But what I do after that and how they take off is super important to me. So inspiring them to really be able to launch startup companies is something I'm very passionate about. Okay, so I guess I have the sort of slide. And so that's kind of, I just wanted to give you a little peek into my life and into my life as a mentor in my lab. As I'll start out first with the, I don't know if I have next slide maybe. Yeah, let's see. Yeah, and this is Amelia Bunnell right there on the right hand, in the middle right there, just recently got married. So my group went up to Tallahassee and we had just a beautiful wedding. Her dad is the local pediatrician there, and this was just a gorgeous wedding. So everybody in the lab is beautifully dressed. Finally, I have a picture that's where everyone is dressed to the nine. Yeah, oh, sorry, it was in green. Okay, let's try that. Okay, perfect. So again, Phyllis asked me to kind of tell you a little bit about what I do in the Office of Entrepreneurship, Innovation Entrepreneurship. And this is one of the things we're actually launching on May 17th at 4. I call it Seeding Startups. That's the one on the upper right. But the idea is, what I really want to do in the College of Medicine for startup companies is I want to create a community that is engaged and is pro-entrepreneurship, right? Since I've been there, I've had, particularly women have called me up and said, hey, I see you've got startup companies. It's women and men, but women in general are a little bit more shy about having startup companies. And they've called me and they said, hey, we're really, we've seen you give this company. What does it take? What can I do? How do I get involved? And it's exciting, right? It's exciting that you're seeding this idea in people who have these brilliant ideas. I mean, what is beautiful about the university ecosystem, which is, to me, it saddens me a little bit that it's under attack, but I think we'll survive. What is beautiful about that ecosystem is basically the university brings you in, gives you money and says, do whatever you want to do to discover something amazing that can contribute to society. And that is such an amazing job, right? No other job can you walk in where they hand you millions of dollars and they say, go crazy. And not only go crazy and benefit society, right? Discover the things that can drive. How else have we made these most amazing discoveries that have contributed to society? It has been through universities that have sparked this. So I also want to sort of in that spirit, I want to excite physicians and scientists to kind of come together and start to work on startup, because ultimately the basic scientist is at the bench and forgets that, wait a second, ultimately what I want to do in our case is, right, it's healing people. It's how do we get this to actually make it into a drug that could potentially heal and help people? And then find a way to combine the physicians and scientists to work together. I have this idea called I2E. So seeding startup on May 17th at 4 p.m. will be the first one. We're going to a local farm, Organic Frog Songs, I think is the farm. And we are actually going to have 10 startup companies pitch their startup to friends, family, colleagues. One of the things that I feel is really sad often is that you have these people who are brilliant and their families have no idea. And a really close friend of mine, should you ever be able to bring him here, his name is Dr. Elias Sayor, beautiful soul. He works on pediatric oncology, on children who have cancer, right? And it's this spirit in this man is just amazing. And his wife and kids, none of them know of his work. And he was my inspiration. I was like, that's it, this needs to end. We need to start having you pitch in front of your families for them to see what you do and how you're able to contribute to your work. And so Seeding Startup is the first one, that, again, May 17th at 4 p.m. And then I'm with Dr. Dwayne Mitchell, another brilliant mind here at UF, a neuro, he has so many titles, I'm not really sure which one to pick, but an incredible in neurosurgery scientist. Also, we're going to do something in September that's called, I forget the name, Startup, oh my goodness. And it's also a day of startup with another billion-dollar company that's gonna come in and potentially put about a few $1 million in a fund to have startups be funded. And so we're pretty excited about this. And then finally, what I'd like to do, and I think it's in the next slide, I highlighted, is it's called I2E, Innovation to Entrepreneurship. And this innovation to entrepreneurship, next slide, sorry. Yeah, I do, or maybe. So, and the innovation to entrepreneurship is basically, is going to be a day of just looking at, yeah, I think it's, yeah. So the idea would be is an entire day of this, and what we'll be doing, and I hope at the end of it, what I'd like to do is actually open up the pitch from these startup companies to the community, and I would be more than happy to sort of extend that invitation to all of you. I think you'd really enjoy it. The idea will be to bring in together a basic scientist and a clinician, and we're going to have something called how many of you, when I say postdoctoral fellow, know what that means? Can you raise your hand? Good, great. Okay, so postdoctoral fellows are basically PhDs who come into the lab and who've already gotten their PhDs, but they work in the lab as researchers. It's almost like a fellowship before they go off to either academia or so on. And my idea is that we can put a postdoc between a clinician and a basic scientist, and we can have them form a startup company, right? And so we got a little bit stuck with the funding, partly because of everything that's happened. I'm not worried about it. It'll happen. It's just a matter of convincing the right people, which it will happen. And it's basically an entire week where I want them to develop this idea that when they've come together, and both with the clinician and the basic scientist, they are now developing a startup company that they can drive in the next couple of years, and we want to be able to fund them for 2 years. One of the biggest issues with clinicians is they are busy. They don't have time to really get on, right, to the basic science, to really get onto the bench. But this takes care of this, because we say, okay, we need you to guide us through this, and we need you to tell us. So Elias Sayor, for example, this man that I mentioned with pediatric oncologist, he's an MD PhD. He's got both the MD PhD, but not many people have these two. Dwayne Mitchell is an MD PhD, right? And those are rare. But if you can bring two of them together, if you can bring a clinician and a basic scientist together, you in essence have formed this exact thing, except with two people. And now with a postdoc between them, you can launch these startup companies. And that's the goal of this. And I think there's something super unique about this. Whoever I've kind of mentioned it has been really excited about this. And so this will happen probably in the next year. I'm trying to get it to have sustainable funding. I did something similar at the University of Arizona, where I had undergraduate students come together in a class. and they were able to do this experiment to try to find a drug within the semester. And by the end of the semester, 6 of them started a company, and I was able to raise $10,000 for them. But it was not sustainable because halfway through, the dean and I raised 30,000 for them. And by the halfway through, the dean was asked me, okay, so what's happening? And I'm like, oh, they started a company to do drug discovery. This is going to take years before we see anything come out, right? But so there was not a sustainable. I had to go to 3 or 4 different or 5 different bodies to get the money, and so that was complicated. So this one, I need what I hope to do is get sustainable funding. I know the sources, and so it's going to happen. It's going to take time. So that's the exciting part about this particular one. Okay, so that's my shtick for the oh wait, there's a green light. Maybe that was the no. Okay, thank you. All right, so I thought I'd also kind of give you an overview of my lab, and what are some of the things that we look at when we try to develop small molecule for neurodegenerative diseases. But again, I want to be please interrupt me at any point that you want. I feel like it's much more interesting when we have a conversation. Okay, so the next slide. I'm sorry. I don't know what's. Okay. Yeah, maybe go forward because I've already shown. Actually, stop. So it turns out that when we're doing research, it does really take a village. In addition to my whole group that works on this, we really have fantastic collaborators all over the world. Thomas Durkin is at the Montreal Neurological Institute. Sami Barmada is the University of Michigan. Michelle Hastings is the University of Michigan. Alison Axman is at UNC, and Curtis Thorne is the University of Arizona, and we recently got funding with TDP-43 and Tau with Michelle Steinhaupt, who actually used to be with me in undergraduate school, and she actually used to pick me up when I was an undergrad on her way into school, and every day she would pick me up. And I think the funniest story that happened when I first came to the U.S., I was walking with her, and somehow I tripped on something and I fell. And Michelle is like, "Oh my God, Mai, are you okay?" And I was like, "Hey, I'm fine." And then she just starts laughing hysterically. And I just stood up and I was like, I'm still like in pain. And she just thought it was the funniest thing to watch me trip. And I later found out that one of the things she amuses her more than anything is people tripping. So that's how we became best friends. And ever since we sort of lost touch, but then came back in touch again. And I'll show you the project where it turns out we had similar interests. And I just think the world is a funny place, right? It always puts people in your path that you wouldn't expect. Did Phyllis tell you all how we met? No? Should I tell them, or is that? So Phyllis looked very upset when she was on the first floor of my building, and she looked very upset. So I walked out with her and I said, "Are you okay?" And she's like, "Well, these kids aren't helping me. I need to park." And it was the coldest day in the past year, like literally the coldest day, and we're freezing. And I said, "Okay, listen. Just what do you need to do?" She's like, "I don't know where I should park." And I was like, "Park where you are. Let's put a piece of paper. Tell the parking people, 'Hi, my name is Dr. May Khanna. I'm the Assistant Dean of Innovation Entrepreneurship. This woman needs to park here. Please don't give her a ticket.'" And so that's how we sort of connected. I put my phone number on there. And so Phyllis and I connected that way. So I think the universe always sends you people, and you should always listen to it and always open your heart to them, because somehow you'll be connected in some way. Okay. I don't think I need to worry about you guys trying to scoop me on my science, or, well, I guess people on if it goes on YouTube, guys, please don't share any of this data. Some of it may be published, and then be kind. That's something that I often try to remind people. All right, so this is kind of a first maybe project that I want to talk to you about, but it's sort of bringing in the idea of how at a molecular level do we think about projects in order to develop drugs for Alzheimer's disease. And so it turns out that NIH had funded a massive amount of labs in the US. I think it was 5 or labs that went in and looked at the brains of patients with Alzheimer's disease and did massive discovery on them to try to figure out what actually went wrong, what are some of the molecular events that are impacted, and how do you define what these molecular events are? So inside our bodies, we pretty much have tiny little machineries, right? That are incredibly fast, right? They're at almost, I don't think lightning speed, but incredibly fast in what they do and how they sort of respond to everything. And it turns out that this particular protein here that I'm showing you on top in orange is called CD44. CD44 is basically a protein that binds to hyaluronic acid. So it's really funny. I gave this talk to my kids' 8th grade class, and I said hyaluronic acid, and the girls were like, "Yeah, we know what that is. We get it on makeup." And I was like, "Wow, that's kind of cool." So yeah, it turns out actually hyaluronic acid is sort of the molecule that these cells respond to when they need to heal your body. And so your skin, that's basically, this is the protein that binds to hyaluronic acid. Hyaluronic acid would be a tiny little molecule right between the ridges right there. I don't know if I can point to, right here in this, between these ridges is where hyaluronic acid would bind. And that protein just kind of hugs it, and then it recognizes that, okay, it's time for me to kind of, to sort of start this fixing mechanism. And what happens is, so this protein comes in, it sticks right to this other protein. This is your cell membrane. If any of you have any questions, please don't hesitate to ask me. So it crosses the membrane and it binds to this protein known as moisin. Moisin is another protein that's bind to F-actin, and that's the protein that basically grabs onto it and says, okay, let's go. And it pushes the protein back, the cell back and forth towards the site of danger. This cell, which I'm not showing the rest of it obviously, is called microglia. It's a cell in your brain that basically is there to help you heal. And so it turns out this is problematic in Alzheimer's because that's highly upregulated. So it's almost like in your brain, for whatever reason, in the brain of Alzheimer's patients, for whatever reason, this is way too high. It's like there is a signal that it can't turn off and it's coming in. And rather than just fixing your dying neurons, it's actually killing more of them. And so this becomes a problem. And that's where that's where we come in with our therapy. And we say, all right, we know that that reason is overactive and it's binding to moisin, the blue. The orange is overactive, it's binding to the blue, it's pushing the cells towards neurons, and you don't want that. So how do we as a lab come in and say, okay, we next slide please. How do we solve this issue, and what do we look at? Okay, so would you mind pressing that play right there? The play, yeah, or just click. I think if you click anywhere, it'll work. Yeah. So here's a protein that I just showed you. That's the moisin protein. I'm only looking at the blue section of that. If you see here that orange, even though we show it as a little arrow, that's actually what it looks like as a peptide, right? The peptide binds in that groove. That's that peptide binding to moisin. And you can see the orange part of it, that's a peptide. That yellow molecule right there, that's us going in and computationally asking what looks like that peptide. It's literally like a key in the hole, right? We know what the key looks like when it enters. What can we replace those little notches with another molecule that would basically kick off this peptide? That's the idea, right? Like we have CD44 is binding, that's that orange. You can see it as an arrow, or you can see it as that's the peptide right there. And that orange, that little yellow molecule, that's our small molecule that's going to ultimately be the drug that all of us are going to take, and it's going to be awesome. That's something we designed, right? So we haven't introduced it yet. We've designed it. We've said, would you mind clicking one more time? Sorry. Yeah, click one more time anywhere. Yeah, oops, go back up. Yeah, oops, upward, sorry. Yeah, click on the screen. Yeah, anywhere. Yeah, perfect. So that we're just saying this is what nature looks like. It's that orange thing sitting on the blue one. And what can we give it to displace that peptide, right? Because the communication is there. They're coming together and they're communicating. And we're asking, wait, how do we stop this? How do we uncouple this communication? And that's exactly what that small molecule does, is it's basically uncoupling the orange peptide from the blue surface, and we're able to disrupt these protein interactions. And ultimately, the idea is that we're cutting off this overinflated communication that we just don't want to have for that's hyperactive. Okay, so I'm just, this is kind of another, this is basically 3 years of someone's life in one slide. It's all of the things that happen. It's way too much detail, but I'm just gonna very slowly just give you, like, not very slowly, I'm not gonna really give you the specific, I just want you to know what we get out of that particular experiment, right? And so what are we hoping to get? What we're hoping to get is when I put this molecule inside the cell, it stops the microglia from saying, okay, I'm going to kill these neurons. That's our ultimate goal. But how do we do this? And how do we prove that we have gotten a molecule that does this? And that's literally what we do in the lab day in and day out. It's a whole bunch of biochemistry, biophysics, animal model studies, right? All of these combined together are about, come on in, sir, don't be shy. It's all about combining all of that in order to try to find some, is this ultimately the drug that's going to do what we actually went out to do, right? Did we find a drug that's going to stop this overactivation? So I showed you this particular complex here. I showed you what we do. We do this thing called in silico docking. We take 1 million compounds to 1 billion compounds, and we in silico on the computer, we model what that small molecule would look like in that interface. That's how we found that small molecule. So once we found that small molecule, the idea is, all right, where does it actually bind to this protein, right? It turns out we can produce these proteins externally. We can purify them. We now have a pure protein that's in our hands, and we can test their binding with a small molecule. So we ask, does it bind? Yes, it does. Remember I told you that the peptide binds to myosin? It's that orange helix that binds to that blue protein. Did we disrupt this interaction? Because yes, it can bind, but does it actually disrupt it? And so we do biophysics and we do imaging. This is a picture of a cell. It does actually disrupt it. We do something that's called NMR. In essence, it's like your MRI, but it's on a protein. So it's an MRI of a small protein, and we can say, where does it bind on this protein? Because as I showed you, we know what that structure looks like. And so can we say where a protein is in essence valleys, and it's literally your mountains and valleys. That's what you get, right? And within those mountains and valleys are opportunities for things that bind and that can actually form a new form a complex. And so we ask, where does it bind? And we can test it. We then take patient-derived cortical neurons. So we sort of know within the brain where that's really affected. And it turns out I can take blood from you, which you guys have probably heard, and I can convert it into pretty much any cell of your body, right? So from your iPS, from your blood, I can deprogram that to become an iPS. From that iPS, I can make it into any cell. And one of the things that we can make is cortical neurons. Now, we're still at the very beginning of how many different types of cells we can do. We can do heart cells pretty easily. We sort of have issues with muscles, but little by little, we are building this way of just, I can take your blood, I can convert it into anything. And ultimately, right, obviously, as many of you may have also heard, cell therapies are the ways that's coming in Parkinson's, right? People are starting to look at taking those neurons and putting them back into the brain. But for us, we just use those neurons to say, did this small molecule have any effect on these neurons? And so that's what we were going to do. And then we test in flies. It turns out those pesky little flies that you chase away from your pesky fruits, I would say next time, give them reverence. They help us out tremendously. We can take flies and we can put a human protein inside of it. So now we're actually looking at a system, at a moving system with a brain, with gut, with muscles and everything, and we can actually test our molecules in this system. It's super powerful, right? And that's without needing to do really anything significant, but we've now just turned this fly into a humanized fly, and we do this with several of the proteins that we're looking at. And what you can see, would you mind moving that the wording out of the way, or on a different window up? Yeah, perfect. So here's the fly brain. And that's the optic lobes, as well as the ventral cord of the fly. And within that, we can start to image different proteins, right? Where are they going along this ventral cord slash optic lobe? And then finally, with my husband's lab, actually, we recently have started looking at mice. I'm not a big fan of mice. I just think like we've solved so many things in mice and it goes nowhere. But it's really useful in order to at least be able to say, did we actually even positively impact, negatively impact? And this is why we start out here. That's human. These are human cells. So in my lab, we always begin with human cells because ultimately, if you can validate it in the human cell, then you have a chance at the animal model. It used to be that people use mice and everything in order to validate these, and I think that's a really big mistake. So that's sort of that's the flow through. We in essence in my lab we have basically a small biotech where we begin with you can start in silico on the computer, but ultimately we go into actual animal studies and trying to define this, and that's really the crux of the majority of the research. I have maybe a couple more slides, but I kind of want to open it up to you guys to kind of have a more of a conversation. Because I get bored of hearing my own voice. It's much more fun to have you guys talk to me and then just ask me anything that you want. Pharma pays me between $500 to $2,000 per hour. So you guys get me for free. That's kind of a really big deal. So you should take advantage of that. Okay, so next slide, sorry. And so I wanted to just kind of show you one more little snippet. One of the things that I've actually started to work on is also women's health. So women's health has been, for far too long, has been ignored. Partly, I don't know why. The world is a wonderful place, but there are some things that we just, we have to improve on. And so in partnership with XChem, who is the CEO of XChem is this amazing woman, Karen Lackey, who kind of introduced me to this and said, hey, why don't we look at this particular complex and how we could help it? So it turns out as women are aging, we lose this AMH hormone and you don't have it as much and you start to have menopause. And it turns out no matter how old you get, and as we're getting older, it doesn't matter. In our mid-40s, we begin to have menopause, which is crazy, right? Like, why are we, it made sense when maybe we were dying in our 40s. Doesn't make sense when we're dying in our 90s or 100s, whatever. So this is where we sort of are very curious about, can we give women the ability to postpone menopause until later? And so we're very curious about this. And the reason I want to show you this is there is on the right-hand side, would you mind clicking on that video? This shows you beautifully. I've shown you so far these gorgeous figures of proteins that my lab works on. And these are all made by Dr. Samantha Perez-Miller in my lab. She's an amazing, she makes incredible figures. But this video right here actually shows you the true nature of what is going on in your body. This is how dynamic, this is how much movement is happening in your body at all times. So when you look at that protein right there and you think it's static and it's not moving, it's completely wrong. It's actually, you are in constant movement and everything in your body is constantly moving. And so I thought this would be a kind of a really neat video to show you. But much like I showed you for Moisen, we're actually doing this for this AMH hormone that's binding to its receptor. We want to ask, in that case, we don't want to inhibit the interaction. We want to increase it. We want to have a better interaction between the hormone and the receptor. And that should at least give us the opportunity to be able to not signal that, okay, it's time to start turning on this menopause period. We want to be able to extend it for at least 10 more years of healthy bones and right? So that's the dream. Okay, I think that's it. I'm going to stop here. Because I just, again, I feel like you've gotten a lot from me, but I'd like to have I'd like to open it up more as a conversation. I don't know what time it is. I don't believe in having a watch, but I'd like to open it up to you guys to just kind of have this conversation. Yes, please.
Okay, I have to take the microphone.
Yeah.
It's only 10:35, so.
Good, great. I could talk for another 25 minutes, but you don't need me to. You've heard enough, my Thank you.
First of all, congratulations on your spectacular graphics. A number of drugs have been started for Alzheimer's and they looked very good in the lab, and then clinically they failed. What have you learned from those failed experiments?
Yeah, Yeah, I think, okay, so I think that as I kind of alluded to, one of the biggest issues is that the animal models I think we're using are not good animal models. And I think people with the, for example, the beta amyloid, right? Beta amyloid, so many scientists kept screaming at the fields, stop studying beta amyloid. It's not the right target, right? Yet pharma kept going and spending billions of dollars. They still went through and put an antibody. Despite the fact that one antibody failed, they still put more billions of dollars for another antibody, right? And so people are stubborn. They don't want to hear they do not want to hear. That's one of the things that I think we do well in the lab. We're actually very much contrarians. I don't believe, if I see something and someone tells me this is what it is and you better follow this path, I almost undoubtedly will go exactly the opposite direction, right? Because I just think too many people rush towards an idea because it's on vogue. And again, this is what's amazing about us as scientists, is that we have to be willing to look at completely different hypotheses. So what we discovered, for example, in the lab, TDP-43 is highly upregulated in Alzheimer's and ALS, and tau is highly upregulated. We discovered that when we combine them together, we actually rescue animals. And so we're very curious about this. But these are two very terrible things on their own, somehow come together, and they are very good. And so we're investigating that. So we're completely open to following things that most people wouldn't necessarily consider as a viable option. So that's what I would say, is we go into very unique directions.
On
I have not lost any of my NIH.
She has not lost her NIH money. Hooray.
Yeah. I'm an optimist, though. I'm an eternal optimist. I just believe that it's going to all work out. We're going to figure this out. And
on your graphic with the blue protein and then the little yellow key,
Yeah.
does the yellow key permanently bind to the blue protein, or
right,
does it have to be replenished
no, that's a great
periodically?
question. It does not permanently bind, but there are ways that you can do them so that they covalently and so they permanently bind. And those molecules have strength and have weaknesses. So in my opinion, I just don't think you should shut something down completely. And I think, by the way, this is one of the biggest issues with pharma. Pharma is very excited as soon as you give them a molecule. They do what they do best, which is make the best possible molecule for that particular space. It becomes so good that you just can't, right? It binds with such high affinity that you shut it down almost completely. And I think that's wrong. I think that there needs to be a certain amount of it needs to be able to bind there, but not permanently, and it needs to be able to decrease it, but not shut it off. And I think that's actually the strength of small molecules that we haven't yet, that's the key that we need to figure out, is how do we make them not super tight, but super specific, and that's important.
I'm so impressed.
You're so adorable.
So Lewy body disease is increasingly diagnosed. Now, it used to be sort of lumped in with a lot of other diseases, but now it's recognized as being its own situation. Does the sort of, specifically, does what you have shown us apply also to Lewy body disease? Because it is a disease of tau, affecting a different part of the brain than Parkinson's, for example.
Correct. Yeah, so for tau and TDP-43, we are most definitely interested in how it would affect other diseases. I'm not familiar with the Lewy body, but for sure there are a few people on campus that I've started to kind of hint at, look, this is what we've discovered. What do you think, and how would it be applicable to your fields? I think people are starting to be very interested in what we're showing. But I think it will move towards Lewy body, but I'm honestly not familiar with Lewy body as much as.
Yeah, well, that's part of the issue, that the researchers are not familiar with Lewy body. My late husband was finally diagnosed with it, but it was almost at the end of his life, whereas for years they were saying, well, it sort of looks like Parkinson's, but it's not really Parkinson's, And so it was very frustrating,
of course,
that I felt that he wasn't being treated appropriately.
Yeah, biomarkers and diagnosis are going to also have to come hand in hand with as we're discovering therapies, and that is actually becoming better. And with I don't like using AI, but with the advent of AI, we are actually going to be much better at diagnosing a lot of things through imaging, through different tools, which we're also developing in the lab.
And any other comments, questions? Well, I have some. Why postpone menopause? I mean, I don't mind not having a menstrual cycle. I really don't. But that means that suggests that women will be ovulating and conceiving late in life, which is not a productive thing, as I understand it. For either older men or older women, we end up with more defective fetuses.
Sure.
And
No, that's a really good point. That's a fantastic point.
you
Yeah.
know, I took Premarin for 5 years.
Yeah.
And then had breast cancer.
Yeah.
But the breast cancer was not estrogen related. It was
Right.
ER negative.
Yeah.
So why can't I have a little bit of estrogen now?
Yeah, exactly. So that's, I don't know anything about this. So that's not at all my expertise. But I 100% I agree with you. This is still very early. So many different aspects of this we're going to have to pay attention, right? The cancer is definitely an issue, because as we sort of increase this, are we increasing our chances of cancer? That's going to be something that we pay attention to. Did we turn on something that's specific for? There are so many issues that are going to come up, but we need to start studying it. I do think that as we're aging more, do we want to have to be able to have a birth? Absolutely not. I do think that with time it does get worse and worse. Although honestly, with a healthy living lifestyle, right, you are probably, it's not, I mean, we get this idea that as you're aging you really can't have children, and because all of your eggs are damaged, etc. I'm not sure that's entirely true, right? A lot of it has to do with also your environment, how you've been exposed, drugs, alcohol, so many things take into account all of that. And I think a healthier living lifestyle also could contribute to actually healthy. And I'm not advocating that children should come, but I think that's an important aspect. But I take periods with no bone loss, right, any day. I mean, I think that's sort of that's kind of the idea of.
Yes, and I'm dealing with osteopenia and
Right.
extreme arthritis right now.
Right. So.
And it's limiting my yeah.
Right. And so at that, because you've sort of had 40 years of or maybe 30 years of not having that kind of accumulates over time. What I'm hoping is that we slowed that down. I'm not saying we shut it off, but at least we slow that process down.
So,
ladies, gentlemen, I know some of you
anything?
are smiling at me through the whole thing, so I know you've got dying questions to ask. Come on.
I've got another quick question. You said you don't care for AI, but AI can help you to
100%.
scan through millions of
We use it.
potential
We
drug,
use it.
drug
Yes.
frameworks and combinations.
Yes.
And so, of course, it's
We're
beneficial.
We're using it. We have to. That's the reality of things. And anyone who wouldn't use it would be at loss of so many different aspects. 100% we have to use it. That's the reality of things. And we use it in several things. We use it in big data. So where I showed you on this flow chart, the very first step in the molecular docking, AI has been introduced, and so we use it there. In imaging, we're now starting to use pattern recognition because we're collecting thousands of images to try to find. We use it there. In the animal models, the flies, when they're larvae, they can turn around. They have all kinds of directions. We also use it. We take videos and we use machine learning again for pattern recognitions and speed and in which directions they're going. Because when we humanize the flies, many of them actually develop degenerative effects that are very similar to the human degeneration. We use it there. So we use it at all steps. It's just that in the back of my mind, it's always kind of like, how do we use this properly? And but it's 100%. It's gonna accelerate. It is accelerating everything that we're doing. That's a true reality.
It's really amazing to me that she's been able to attract funding for these projects.
Why do you say that? TDP-43 is huge. The biggest funding that I have is through TDP-43, and it's an ALS, it's an Alzheimer's. The women's health, that's a private partnership, and that's where that's going to be a different funding stream. And Batten is, the Lermans were a family whose grandchildren have Batten disease, and so they approached me, and they've given money from their own funds.
When you do your research, do you stress animals or flies, for instance, to the point where they're showing Alzheimer-like
Yes,
symptoms
yes.
and then
Yes.
try to see what happens when
Yeah.
you inject the drug?
Absolutely. That's exactly what we use it for. And it's a lifetime, it's a lifespan that's so short, right? Instead of, for example, mice that takes months, it takes exactly a month for fly. Within 2 weeks, we already have data. That's huge, right? And so we can accelerate so much of that in again with a system where you're taking any of your proteins of interest and CRISPRing into the fly. So you've now humanized that fly. Right, with that particular protein, and then we can sort of, it's very exciting.
So the next time you go to smash a fruit fly,
That do not, please keep that fruit fly. Yes, don't. I mean, I'm not sure if you want to save it, but at least, like, again, right, just kind of remind yourself. Mai told me you are cool. I'm not attacking you. Literally, those are the fruit flies that we use in the lab. It's very, very cool.
and think of how tiny their little brains are,
Tiny.
and yet we can work with them.
Yes, we
As-
have microscope. We handle them. They dissect the brains. They dissect the spinal cord. It's very cool. It's very exciting. I know.
Okay, well, thank you all very much for coming, and thank you, Dr. Khanna.